Also, thank you for again for organizing this seminar. It's a great service to the community, and thank you all for coming. My talk certainly has intersection with several previous talks. So let me start. I will consider the non-local analog of Calderon's problem. So let me start making a brief summary of Calderon's problem. I think most of you know already. The question is, can you recover the electrical conductivity of a body by making voltage and current measurements on the boundary? And the mathematical community is Calderon's problem because he proposed perhaps the first mathematical formulation of the problem motivated by your physical prospection. An application that interested me in this problem, potential application, is early breast cancer detection because of the contrast between normal breast tissue and cancer of breast tumor. And in general, this is a very ill-posed problem because the currents go in everywhere immediately. It's a very diffuse inverse problem. There is no high resolution. It's a very ill-posed problem, but it makes it more interesting mathematically, at least. This Calderon smiling. I tried to find a picture where he's smiling because most of the pictures you have seen, he's very serious. He liked to dance the tango and drink Argentinian wines, Malbec in particular. Also, I always mention this quote from his speech at the Universidad Autónoma de Madrid when he accepted the doctor honoris causa. In my work at Yacimientos Petrolíferos Fiscales, YPF, which was in the 40s, was very interesting, but I was not well treated. Otherwise, I would have stayed there. So it was a great fortune for mathematics that Calderon was not well treated. Apparently, he was reading Kuratowski's topology book, where he was supposed to be working in the laboratory. A more recent application that also has been of interest to me is imagining stroke with EIT, because EIT is a general method which is good for contrast. So when there is a clot, of course, in the brain, there is a low conductivity, and hemorrhage has very high conductivity in the case of a stroke. But the problem is that the symptoms are very similar. This is a difficult problem because of the skull is an inclusion and there is another inclusion inside. So there is an inclusion within an exclusion. And you don't know the medium surrounding the clot or the hemorrhage. So we have developed, at least theoretically, some method to find this, whether it's a clot or hemorrhage. So this is an important problem. For instance, one would like to have in an ambulance, an emergency ambulance, a quick method to detect which one you have, because the treatment is different in both cases. So this is a picture that has been obtained using some of the methods that I will explain today is with Alan Greenleaf, Matilazas, Mateo Santacesaria, and Samulis Iltare. Samulis and the group at Helsinki had been continuing trying to do this in practice. And this is the method that we have developed is similar to, is much related to X-ray tomography. We can relate it. Here you see on the left is conductivity 1, and in the middle is a very low conductivity and very high conductivity on the right. Okay, so this is well known, so I will go very quickly. The current by Ohm's law is given in this form. High conductivity is the inverse of the resistivity. There are no sources of sinks of current. The divergence of the current is equal to 0. And the information is given by the Dirichlet-Neumann map, which maps a voltage potential on the boundary, F, to the induced current flux at the boundary, which is the normal component of the current. So mu is a unit outer normal. And the inverse problem, and of course this is an idealized version, thus the knowledge of the Dirichlet-Neumann map determines the conductivity. And the Dirichlet-Neumann map shows up in many other places in mathematics. And let me review very quickly some of I cannot mention all the results, at least the result that started me on this subject was a joint work with John Sylvester many years ago. For a smooth enough conductivity in C2, there is uniqueness. If the measurements are the same, the conductivities are the same, and the regularity of the conductivity has been extended, and the latest results is for conductivities was one derivative in Ln by Haberman in dimensions 3 and 4. This is a very nice result. And one expects that this perhaps is optimal in any dimension. And Caro and Rogers have shown that the uniqueness is valid for an important case, which is Lipschitz conductivities. So in dimension 3 or higher is believed that this is optimal, but for conductivity that show up in practice, the uniqueness should be true, for instance, for piecewise smooth conductivities. But nobody has been able to prove any result below one derivative in dimension 3 or higher. And Nachman developed a reconstruction method that's based on the same ideas of the uniqueness proof. It uses what's called complex geometrical optics. Alessandrini gave logarithmic type stability estimates. That means the two Dirichlet-Neumann maps are close in certain sense, then the conductivities are close. But it's very ill-posed problem. It's a logarithmic type of stability. But that's the worst case scenario. And numerical methods and practical applications have developed, especially by David Axelson, Hamilton, Nunce, Siltanen. I should have mentioned Margaret here. Sorry about that. In the two-dimensional case, there is the first result was by Nachman for C2 conductivities in 96, and it was improved to one derivative, but the seminal result is by Stalans and by Barinta, who were able to prove this result for bounded and measurable conductivity, which is the best possible in some sense. The case of C2 conductivities follows by a result of Buchheim, who proved that for a general potential, one can also define the Dirichlet-Neumann map, then the potentials are the same. The proof of Buchheim works for C2, C1 conductivities. In principle, he claimed it for L infinity, but the proof only gives C1, and this was improved by Blasten, Immanulov, and Yamamoto for L infinity conductivities. Okay, so the reason for the smoothness required in the conductivities is this reduction, this Liouville transformation that reduces the problem to the case of the potential that I mentioned already. In this case, there is a unique solution of the problem if the potential is of this form. And one can pose the problem for a general potential, even complex value. In the as long as the Dirichlet problem has a unique solution. So 0 is not a Dirichlet eigenvalue. One can define the Dirichlet-Neumann map in that case. And so this reduction from the conductivity to the potential involves already two derivatives of the conductivity, and that has been the main reason in dimension 3 or higher why some regularity have been imposed. The less regularity, the more singular the potential, and that leads to complications, technical complications. And the proofs, most of the proofs are based on this, was something called Alessandrini's identity, but it's just simply the Green's formula. Q1, U1 is Laplacian U1, Q2, U2 is Laplacian U2. If the UI solve the equation, and you get the boundary information. The importance of this formula is that this is linear in Q. Here, the nonlinearity of the problem comes up in the U1 and U2. Here, that depend on Q1 and Q2. So, for instance, for stability, for uniqueness, of course, this is 0. Lambda Q1 equal to lambda, this is 0. But for stability, you apply the same type of ideas. I mean, you have, these are closed, then you will prove that the potentials are closed in some sense. And the reconstruction method, if Q2 is equal to 0, for instance, then you can have a formula to relate the information inside to the information on the boundary. This is a very useful identity. And in the case of uniqueness, this is reduced to proving that there are many solutions of the equation so that the products are dense. So I'm going quickly because I know this is material that probably most people know. And the method, most of the methods in dimensions 3 or higher that has been used for uniqueness and reconstruction and stability is these complex geometrical optic solutions. So there are solutions that behave like these exponentials that were considered by Calderon himself for the linearized problem, plus a term that goes to 0, rho goes to infinity. So how fast goes to 0 depends on the regularity of the potential. For instance, for L infinity, bounded potentials, this is the case like 1 over modulo of rho. So for more singular potentials, the decay is different, and this leads to the technical complications of lower regularity. But this replaces waves for elliptic problems. We don't have waves, but this is a replacement. For hyperbolic equations, we have real geometrical optics. These are oscillating functions and so on. So, but these can grow exponentially, can decay exponentially, or can oscillate. So my talk is really more related to the anisotropic case because I'm going to consider the non-local anisotropic problem. So let me review quickly the case that this is a positive definite symmetric matrix. The same map, we have the same map as before, the Dirichlet-Neumann map, which is given here. But now we're trying to recover a full matrix, which is 1/2 n times n plus 1 functions in any dimension. And the question is whether you can recover the conductivity in this case. And the answer is unfortunately no. And this is due to the invariance of the equation and the changes of variables. If you have a change of variables, a diffeomorphism, which is the identity at the boundary, then it was called the push forward of the conductivity, which in terms of matrices given by the Jacobian transpose composed with gamma composed with the Jacobian divided by the determinant gives exactly the same information. And the group of diffeomorphisms, which is identity at the boundary, is infinite dimensional. So there are many conductivities that give you the same, exactly the same information. For instance, any rotation inside is an example. As I said earlier, this can be seen by just changing variables into the solution of the equation. This seems to be bad news, but in general, we know something a priori about the conductivity, even if it is anisotropic, and then you might be able to find this change of variables. For instance, in the case that this is isotropic, the push forward is isotropic, and gamma is isotropic, one can prove that the diffeomorphism must be the identity. So in that case, as we have shown before, you have uniqueness in the isotropic case. But there are other cases where you know something a priori that fixes the change of variables. But the question is whether this is the only obstruction. Is there any other obstruction to uniqueness? So this is one of central questions that remains open in inverse problem. There are some results that I will mention quickly, but this is also a geometric problem. One can consider it on a compact Riemannian manifold with boundary. Take the Laplace-Beltrami operator, and local coordinates is given by a positive definite symmetric matrix. In coordinates, again, is given in this form, the Laplace-Beltrami operator. On a manifold, you're not familiar with manifold, you can think of a domain with a positive definite symmetric matrix, which is the conductivity. The connection with the conductivity is that this is the square root of the determinant of G times the inverse. G upper Ij is the inverse of the matrix G. And in coordinates, the Dirichlet-Neumann map is given like this formula, because we have the square root of the determinant also here. In geometric terms, this is called the conormal derivative with respect to the metric. And this question of on manifolds is also arises in holography. The question is whether you can recover the bulk. It's called the bulk, the manifold, and the metric from, in the case of the Dirichlet-Neumann map, is the boundary, it's called the boundary two-point function. It's like the Green's function, outgoing Green's function calculated at the boundary. That's in other words, is holography, because the question is whether you can represent, say, a three-dimensional world in 2 dimensions. You can give the Dirichlet-Neumann map, but there's other information that you can impose on the boundary. For holography, for instance, the distance function. And these physicists have considered this question. So it's not just in the inverse problem community that this is of interest. And what we know is very little, except in dimension 2. So if you have a result with multilassers in dimension 3 or higher, a manifold which is real analytic, connected compact with boundary, you can take a subset of the boundary as small as you want. It's real analytic. Assume that the Dirichlet-Neumann map is the same. This is even a local result. You measure on part of the boundary, F is supported on part of the boundary. Then it's true that the metric is pulled back of the other. So metrics pull back and conductivity is pushed forwards, the inverse. So one can solve completely the problem in the dimension 3 or higher in the real analytic case. In fact, you don't need to know the manifold. You just need to know the boundary and the Dirichlet-Neumann map, which is information at the boundary. But the main problem is, the main assumption is real analytic, which is not realistic. In dimension 2, one can prove a much better result. In dimension 2, we have isothermal coordinates. In fact, there are many more complex geometrical optics solutions in dimension 2 than in higher dimension. In 2 dimensions, in the same situation, you have any surface with compact Riemannian manifold with boundaries. You take a subset, non-empty, of course, I should have said here, and you have the same information. In that case, you can solve the problem completely. There is an additional obstruction in dimension 2 because the Laplace-Beltrami operator is conformally invariant. That means you take a multiple of the metric, that there is a multiple that comes up. So the solutions for the multiple of the metric or the metric are exactly the same. It's conformally invariant. So there is a conformal invariance additional. So you can prove, in fact, that those are the only obstructions. And you can recover the topology of the manifold as well. So in dimension 2 is the problem has been solved, at least in the C infinity category for manifolds. And let me mention an interesting recent result this is in dimension bigger or equal than 3, Daudet, Camran, and Nicolas, where they have partial data. That means F is supported in an open set of the boundary, and you measure in the same subset. Gamma it can be the whole boundary. You can think on the whole boundary, but it's even true in this case. Gamma is smooth in the interior, but only held up to the boundary. And then it's not true that this is the only obstruction, the pullback. And this is actually not a complicated proof. It's based on Miller's counterexample for unique continuation. It's a unique continuation from the boundary, meaning if you have the Dirichlet data vanishes on the piece of the boundary and the Neumann data vanishes on the piece of the boundary, on an open subset of the boundary, then the solution must be 0. So in dimension 3 or higher, there are counterexamples. If the conductivity or the metric is only C alpha up to the boundary, it can be smooth in the interior. In dimension 2, there is no such counterexample. Unique continuation from the boundary is true for any, even L infinity conductivity or metric. So this is a connection with unique continuation, which is interesting. Okay, so this ends, but before I continue, let me mention this problem that I have been displaying a lot. And in fact, I have offered a small amount of money, $1,000 to anybody who can solve it. I don't want to take it to my tomb. You take two anisotropic conductivities, assume that the Dirichlet to Neumann maps are the same, then there is a diffeomorphism, so that which is the identity of the boundary, so that one metric is the push forward of the other. Okay, this is the method that we have been using for the isotropic case, which is complex geometrical optics, does not work in the anisotropic case in dimensions 3 or higher. In 2 dimensions works because you can transform an anisotropic conductivity to an anisotropic one using isothermal coordinates, but it's not. This is not the case in dimension 3 or higher. So especially for the people who have not tackled this problem, they can look at it with fresh eyes and maybe they have a new idea how to do this problem. Okay, so now we go to the non-local case. I'm going to consider the analog problem for the non-local operators. And the title of this talk is that you have non-locality that helps to solve the inverse problems. So the typical non-local operator is a fractional Laplacian. So this is, for instance, the square root, which is an important example, minus Laplacian to the 1/2. And this can be defined by the Fourier transform. The Fourier transform you apply to a function f is modulo c to the 2s times the Fourier transform, take Fourier inverse. So it's a convolution operator. Therefore, this operator is non-local. It does not preserve supports. And computing this involves values of u far away from the point x. So this type of fractional operators arise in many situations when you have non-local interactions. And something that happens in Chile, where I am, affects what happens in US, for instance. And the fractional Laplacian arises as the steady state for different models for diffusion. For instance, for the standard heat equation, is normal diffusion, Brownian motion. The case of super diffusion is in the probability is called Levy flight. Is this case, as this is the case that I'm going to consider, the second case. Not there are many situations where this is subdiffusion, where the fractional power is on the time derivative, and you can have a mixture fractional and time derivative and the x derivative. I'm essentially consider fractional in the x derivative. So the fractional Laplacian is related to anomalous diffusion, as I said before, involving long-range interactions, turbulent medium, population dynamics, which have some change in some places affects everything. Levy process in probability theory, as I mentioned before. These are infinitesimal generators of some Levy processes and financial modeling with jump processes. And I'm not going to talk about the third case, which is fractional in time. There is a very nice book by Kaltenbacher and Randell where they consider this type of inverse problems. So this is the simpler model, perhaps, the simplest model. You take a bounded domain and it's L infinity function. This is like we were considering before, Laplacian plus Q, but now S is between 0 and 1. And the Dirichlet problem that we're going to look at is not the standard, because this is now a non-local operator. So solutions may blow up at the boundary or may decay not in the standard way. You cannot solve in general the Dirichlet problem, the usual Dirichlet problem. So we solve the problem in the exterior. So this is information in the exterior. And the Dirichlet to Neumann maps depends on S, maps HS of the exterior to H minus S. And is defined as the fractional Laplacian of U restricted to the exterior. The reason for this is that this is the analog of the normal derivative. You can prove if you take this quantity and as you approach the boundary, it is from the exterior, it gives you the normal derivative. So that's why it's the analog of the Dirichlet to Neumann map. And the inverse problem is given this, so you fix the S, given this map, can you recover the potential? So the problem is the following. You have a certain process in the interior, and you measure it in some Levy process usually, and you measure it in the exterior. The question is, can you recover the process? The process in this case is given in this form. There are other types, as I'm going to consider later. And the basic result is that this is the case. There is uniqueness, and there is, there are many other results, stability, reconstruction, and so on. So you take two potentials and two open subsets of the exterior, arbitrary open subsets, can be as small as you want. And the Dirichlet to Neumann maps are the same for functions supported on one open set and measured in the other, then the potentials are the same. And in fact, you only need to have one. I will mention this result a little bit later. Only one F is enough. But let me consider first the case of many measurements, infinite number of measurements. So this is a result which is involves local data for arbitrary open sets. There is no difference in the dimensions. This is true for any dimension. I should have said here, bigger or equal than 2. And it's a new mechanism that does not use complex geometrical optic solutions for solving this type of non-local inverse problems. And one also is going to prove, one proves if this is the case. Let's assume that you have it in the whole exterior at the moment. I just want to explain one thing about this, is that you have this identity, which is when this is equal to 0, is also going to be true for the fractional Laplacian. This is proven by using just Fourier transform. U1 is the fractional Laplacian, and so on. And what we used before is the complex geometrical optics to get that the products of solutions are dense. But now, using the non-locality, we're going to approximate this fractional, the solutions of the fractional equation by any function by using the Runge approximation and for non-local operators. The Runge approximation is the same as unique continuation. This was observed by Lux and a long time ago. So let me say briefly about the Runge approximation. The classical Runge approximation is for analytic functions. You have an analytic function in a simply connected domain, can be approximated by complex polynomials. For elliptic PDE, any solution, I forget to mention Lagrange, any solution U, an open subset of omega can be approximated using solutions in omega. And this is reduced by duality to the unique continuation principle. So they are equivalent, in fact. Lux and Lagrange observed this in 56. The Runge approximation produces solutions which in some open subset are approximately 0, and another one they are very large. But outside these open sets, there is very little control. That's the problem. Of course, they are useful in some cases, and this has been used for the Calderon problem for boundary determination. Conan-Vogelius was one of the first results. They prove that you can recover from the Dirichlet to Neumann map all the derivatives of the conductivity at the boundary, and they use this method, and in particular for piecewise analytic conductivities. They show uniqueness for piecewise analytic conductivities using the Runge approximation. We use it with Habib Amari to show that you can recover conductivity if you not the Dirichlet to Neumann map in an open subset of the boundary, as long as you know the conductivity near the boundary. So we use the Runge approximation to continue to the interior, detecting shapes of obstacles. There was Isakov, Ikehata developed the probe method using the Runge approximation, oscillating the Gaussian solutions. There are several things that use this Runge approximation, very useful method. And so the unique continuation, which is the Runge approximation, is much stronger for non-local operators. And this is a key why the non-locality helps. If U is in H-R can be quite singular, and U vanishes in an open set, and the fractional Laplacian vanishes in the same open set, then it must be identically zero. And this is not true. It's definitely not true for local operators. You can have a compactly supported function which is non-zero. U is zero, the Laplacian is zero outside the support, but the function is not zero. But this is the case for non-local operators. And the proof of this, I'm not going to give the details, uses the famous Caffarelli-Silvestre extension of U, which when you lift, in order to understand the fractional Laplacian, Caffarelli-Silvestre realized that you can go one more dimension, consider the upper half plane, and consider the Dirichlet problem for the in the upper half plane solution with data and y equal to 0, but with this factor 1 minus 2s. And the fractional Laplacian is obtained from here. So it comes from this local equation. This is like the normal derivative of the solution. This is the fractional Laplacian. In the case s equal to 1/2, which is a very important case, is the square root here, s equal to 1/2, this is the standard Laplacian. And then one uses, so that you get a local, from the non-local, you go to a local equation, but with a weight, with a degenerate weight in the general case, when s is not 1/2. It's called an A2 weight in harmonic analysis. And Uhlmann proved Kahneman estimates and unique continuation for this case. And that's what one uses. It's a very nice paper of Uhlmann and open up the field. The Caffarelli-Silvestre extension is just it's a generalization of this simple fact that for a sufficiently regular function W, you have the Dirichlet problem in the upper half plane. You can write the solution explicitly, the coordinates x and y here. And then the Dirichlet-Neumann map is simply the fractional Laplacian, because you get modulo c. You take y going to 0 with the minus sign, which is what we have here. The fractional Laplacian is obtained as the normal derivative of the solution of W. So it's an extension for every s. This is the case s equal to 1/2. And so we use this to prove the following approximation result, which is the Runge approximation. Any function in L2 can be approximated by solutions restricted to omega of the fractional Laplacian. Okay, we can do also, this is this infinity case. You can also do the CK case, but let's do this infinity case. You apply it to So the identity is the same if the Dirichlet Neumann maps for the fractional Laplacian are the same. By using Fourier transform, you can easily prove that the identity is the same. So now you can approximate this by any function. This is something I mentioned before, but I want to emphasize. You don't need complex geometrical optic solutions because you can approximate any function here, and then this is orthogonal to any function. Therefore, it must be 0. So Q1 is equal to Q2. But this is the main fact, which is not true for harmonic functions, for instance, that any function can be approximated by harmonic functions. This is true because you have a non-local operator. So let me discuss the anisotropic case. For some progress has been done in the anisotropic case in the fractional case, and this is a very nice result of Gauche, Lin, and Xiao. So when you take a positive definite symmetric matrix, this is the case that we had before, but now it's fractional. So I should have said here S is between 0 and 1. And you also define the same Dirichlet Neumann map by using this L is this operator U restricted to the exterior. You can define the Dirichlet Neumann map. And then they prove that you can recover, determine uniquely Q from knowing this map. And this is definitely not known in the case S equal to 1. In the local case, we don't know even that result. In that case, we know gamma, but we want to recover Q. And also that's unknown. So the non-locality helps. This is perhaps one of the main instances where one shows that the non-locality helps. We had some indication before for partial data. This is the operator, as I mentioned before, LS. That's the Dirichlet Neumann map restricted to the exterior. And of course, in this case, you don't have the Fourier transform to define the fractional Laplacian, the fractional operator in this case. And this is something that I'm going to use in a moment. Using the heat equation. This is proven by using the spectral theorem. You can use the heat equation. This is a solution of the heat equation with this power here depending on S. You can use other representations, of course, but the heat equation is particularly useful, and that's what they use, and also they prove the Runge approximation in a different way. Okay, so this leads me into the second instance where we have the anisotropic case, which is the case of manifolds. So now we'll finish with this. So you take now a smooth closed manifold, not the manifold with boundary. You take the Laplace-Beltrami operator on M. This is now positive with the minus sign. And it's a self-adjoint, and you can define by using the spectrum. In the case, the spectrum is discrete, denoted by lambda k here to the alpha, and these are the projections of the function on the eigenspaces. The orthogonal projection onto the eigenspace of lambda k. So this is the way to define the fractional Laplacian in that case. And the inverse problem that we are going to look at is the following. So first we solve is the source to solution map. So we have a source. In order to have a unique solution, you need to assume that F is orthogonal to constants. And then there is a unique solution of this equation and can be written in terms of the negative fractional power. Yes, it's essentially Fourier series. We solve here. And we define the source to solution map. So we have data F supported in this open set, which can be arbitrarily small. It's any open non-empty set of the boundary, and we define the solution of the equation in these open sets. So this is the source to solution map. So the fractional anisotropic Calderon problem is whether the knowledge of this map, knowing the observation set and the metric in the observation set, determines the manifold globally up to this isometry, up to this change of variables. Of course, there is this obstruction as well. You take a diffeomorphism and you have take a metric which is the pullback of the other and is identity in the observation set, then the Dirichlet to Neumann maps are the same. And the theorem, I see this typo here, Uhlmann, I think has only one. The theorem is that there is uniqueness up to that obstruction in that case. So you take two smooth, close connected Riemannian manifolds of dimension, and you take an open subset. I assume that you know everything about the open set. In fact, I think you can actually recover the metric in the open set as well, but this is, let's assume it. And you have the Dirichlet to Neumann maps are the same. Then there is a diffeomorphism that pulls back one metric of the other, and the diffeomorphism is the identity in the observation set. And so this, in the anisotropic case, we don't know the result, even in a smooth, closed Riemannian manifold. We don't know it. And as I mentioned, in dimension 2, there is a conformal invariance for the standard Calderon problem, but in this case, this is not conformally invariant. There is no such obstruction in the two-dimensional case. And the method of proof uses the heat equation. So one first proves that if the Dirichlet to Neumann map for the fractional case, this is the fractional anisotropic case, then the heat kernels for the two metrics in the open set must be the same for all t. So you get an additional time, an additional extra time here, which seems not to be present here. So the heat equation is the same. And then from the heat equation being the same, we will show that the wave equation is the same. And then one applies the boundary control method developed initially by Belychev, Kurilev, and several other people to show that the metrics are isometric. And so as I mentioned before, the fractional Laplacian can be written in terms of the heat equation, and this is the key. That also was used by Bosch, Lin, and Chow before. And if the metrics are the same, then the local operators are also satisfy this. And now you can apply, because the support is contained in O, you can apply the fractional to the powers of the Laplacian, to any power of the Laplacian here. Okay, so this is true for any power here because this is a local operator, because there are some technicalities, and then we get this identity. And then we use the fact that any power of the operator is simply the time derivative of the heat equation, and then you just integrate by parts. Well, of course, we need the decay of the heat kernels at infinity, and we need to check that everything works at 0. And for that, you take open subsets so that they don't intersect. This is in order to have the decay, exponential decay of the heat kernels. You take any two open subsets so that they don't intersect. So the heat kernels decay exponentially in that case because the distance is positive between the two open sets. And then you have the estimate for the heat equation. And I'm going a little fast here, and you just integrate by parts. You can check the integration by parts is valid. And so you have that this function phi of s is phi of s, the moments of this function are 0, therefore phi of s is 0, and this easily implies that the heat kernels are the same. For any open subset, this is W2 is arbitrary. We constructed the W1 so that it has no intersection, but at the end of the day, we have the heat equation for any open subset of O, and so you have this identity. And then once you know that the heat kernels are the same, this is just a trick of integrating by parts and getting the moments of this function here. Knowing that the heat kernels are the same, you can prove that the wave kernels are the same. And for the wave equation, you can define the source to solution map for the wave equation. So you have this, and then there is, as I mentioned before, once you know that the wave kernels are the same, there is a consequence of the boundary control method of Belishev, Kurilev, and so on, which relies on unique continuation theorem of Tataro. Then the two metrics, one is the pullback of the other when the diffeomorphism is identity in O. And one uses this connection between the heat kernel and the wave kernel. So this is the solution for the wave equation. And there is a transmutation formula of Kanai that relates the heat equation to the wave equation. And so you get that the wave equations times this factor is the same, and then some Laplace transform of the wave kernels are the same. And therefore, inverting that you get that the wave kernels are the same. The reason, maybe one can prove it directly from the heat equation, that the heat equations are the same, but since we have this powerful technique for the wave equation of the boundary control, one can use it. And this is the sketch of the proof. Yeah, let me just finish. I'm already out of time. Sorry to go a little fast at the end. To show that there is a recent result which shows that the Dirichlet theorem map of the Cauchy data for the non-local operator that we have been considering, then you can recover the local Dirichlet theorem map when S is equal to 1. So at the boundary. So all the results that are known for the local case apply to the non-local case for this type of operator, isotropic or anisotropic. So I'm not going to have time for that, but there are many further results, stability, Ruland and Salo, one measurement and a reconstruction method with one measurement, local perturbations of the fractional Laplacian, like a magnetic field, things like this, non-local perturbation, fractional magnetic operators. This is Lee, Covey, and so on. Fractional parabolic, fractional elasticity. There are many. I'm not going to. Probably I'm not. I'm missing some important references, but there has been work. Has been a lot of activity in this direction. So let me finish with this. Thank you.
Thank you very much, Gunther, for the very nice talk. Oh. Please continue. Sorry.
No, I'm finished. I have a couple of questions. Whether you can recover in the case in the fractional case for the anisotropic conductivity, whether you can prove that you can recover up to this change of variable, which is the identity in the set where you're making the observation, is not known. We prove it for closed Riemannian manifolds, but not for the case of complete manifolds. And a very intriguing question is whether we can go from the non-local to the local. There is the question of whether one can go from the local to the non-local and then applies the result for non-local. And another question that has arisen in this, John Schottland has mentioned this question, whether one arises in quantum optics, whether you have inverse scattering. We consider inverse boundary type of problems or with measurements on the exterior, but how about infinity inverse scattering for the fractional Laplacian? So these are some of the questions that are not known at the moment. Now this is the end.
Thank you very much. Thank you very much, Gunther, for the very nice talk. Are there any questions or comments, please? Any questions or comments, please? Please feel free to unmute yourself.
I went over time, sorry.
No, it's good. Very good. Any questions or comments, please? Gunther, could you please say just a few words about the idea, of the proof of your result passing from non-local to local? Sorry.
Okay, it's using the, let me, I don't have the slides, and can you see my slides?
Yes. You can go for full screen.
So let me briefly mention okay, so this is the case of non-local data, and consider the Cauchy data in actually in an open subset of the exterior. Doesn't have to be the whole exterior. And consider U in measuring the exterior and the fractional measuring the exterior. And the theorem, I didn't have time to talk about this, is that if the Cauchy data is the same on this open set, then the Cauchy data, meaning the solution and the normal derivative for the corresponding local operator, LK is the same. So you can go from the non-local to the local. And the idea of the proof is to use the Caffarelli-Silvestre extension again that I mentioned earlier. And consider, so this is the y1 minus 2s that I mentioned before. This is the fractional, the Dirichlet-Neumann map for the fractional operator. And one consider this function v, which is the average on the line for y bigger or equal than 0, this term here. And one can prove that knowing the Cauchy data for the fractional operator, one knows the Cauchy data for this, and then follows from the fact that V at the boundary is dense. So all of this information, U tilde corresponds to the fractional case, is dense in H1/2 of the boundary. So that's the crucial element of the proof. Sorry, I cannot give more details now, but it's...
Thank you very much. It's great. Thank you so much. Thank you so much. Are there any other questions or comments, please? Any questions or comments, please? Okay, if not, thank you very much, Gunther, for the very nice talk. Thank you very much. And thank you very much for everyone for coming. Thank you so much.
Yes, thank you all for coming from Chile. I'm in Chile right now.